Up until this point, when we've solved an equation, we've looked at a point that satisfies that equation. An x and y coordinate that when you plug in to the equation, you get a number equal on both sides. That means it satisfies the equation. Well, for solving a system of equations, we're given two equations, and we're still looking for a point that satisfies an equation, but not just one. We're looking for a point that satisfies both equations. In this case, we have multiple different ways we can solve. We'll look at graphing. We're going to look at algebraically and see which one fits our style. So first we're going to talk about graphing. And graphing shows you what it actually means to have a solution to a system of equations, what it looks like. And that's important to know. However, graphing isn't always the best option because it has to be an exact intersection on what we call a lattice point. So right here, like where these lines intersect, where these grid lines intersect, these are all called lattice points. And we use lattice points, specifically because it's really easy to tell, okay, it crosses right at this point. If I have a line that crosses in the middle of that box, I can't be for sure exactly where that's at. And you'll see what I'm talking about. So let's graph these two lines. They're already in slope-intercept or y equals mx plus b form, so I can graph them fairly quickly. The purple one, I can tell that the intersect is going to be 0. The y-intercept is going to be 0. And my slope is 5, so I go up 5, 1, 2, 3, 4, 5, and over 1. Or I can go down 5 and over 1. And I'm going to attempt to draw a line that connects these. Not the, okay, that's horrible. Let's try that again. That's also horrible. It isn't as easy as it looks to do on this computer. Alright, that's close enough. And now I'm going to draw a line for the other one, which I don't have that color for some reason, so I'm going to use red. Intercept is 4. Right there, and my slope is 1, so I'll go up 1 over 1. And you can see right off the bat that our intersection is going to be right there. This line is easy to draw. Okay, so there are my two lines. This line is y equals x plus 4, and this line is y equals 5x. And you can see that the intersection is right here at that lattice point. And that point is 1, 5. So the values that satisfy both equations are x equals 1 and y equals 5. If I were to plug both of these values in to these two equations, I would get a number equal to another number. And just to show you that it works, if I plug in 5 for y, it's going to equal 5 times 1, and that's 5 equals 5. So that works. And here if I plug in 5 for y, that equals 1 plus 4, which is 5 equals 5, which that also works. So you can see I get the same number on both sides. That means my equation is true, it's satisfied. But like I said, if you have two lines that cross, say, like this, and say that's their intersection, I don't really know what that point is. It looks like it goes over 1, 2, 3, maybe 3.5 in the x direction, but it could be, it could be 3 4/7. It could be somewhere along there. I don't really know exactly what that is. It could be 3.4, it could be 3.7. I don't know. Therefore, graphing isn't the most efficient way to solve. Graphing shows you what it looks like when those two lines intersect. And that is the one point that satisfies both lines, and that is only one point right there. But we can always find a solution when we solve algebraically. So let's look at some ways to solve these algebraically. The first way is substitution, and substitution is exactly what it says. I'm going to solve for a variable, and I'm going to substitute that in, and I'm going to find out what that variable equals, then plug it in, find another one. Substituting. You're used to substituting numbers, you plug in a number, and you evaluate. That's all this is. So in my first example, I already have it set y equals. So there's two ways I can solve this. I can take the fact that y equals 5x and plug that into my second equation. So every place I have a y, I would plug in 5x. That's one way to do it. So let's try it that way. So I'm going to take 5x and I'm going to plug it in for that y right there. So instead of y, I'm writing 5x equals x plus 4. And I'm just going to subtract x from both sides. Get 4x equals 4. So x equals 1. This is the same problem from the first graphing example. So we already know what the answers are. I'm just showing you that you can verify it algebraically also. So x equals 1. That's our first coordinate, which we knew. Now to find the second one, I'm going to take the fact that x equals 1 and plug it into either equation. So let's just use, we'll use the top equation. So y equals 5 times 1. So y equals 5. So my point is 1, 5, which is what I found out earlier. Algebraically was probably faster in this case. Example number 2, I don't have an equation that's solved for a variable specifically. So I got to kind of look at it and see which variable it would be easiest to solve for, and then substitute that in. So if I'm just looking at this, take a quick glance, I would say that I would solve for y for the first equation because it's one step and I'll have y equals a number. So I'm going to add 3x to both sides here, and now we get y equals 3x plus 2. So now every place that I have a y, I'm going to substitute 3x plus 2, and that's going to give me an equation in one variable, and I can solve for x. So I got 8x minus 15 times y. Well, I know y is 3x plus 2, so 3x plus 2 equals 7, and now I'm just solving for x. So 8x, and I'm going to distribute, so minus 45x minus 30 equals 7. I'm going to add 30 to both sides and combine like terms. So 8x minus 45x is negative 37x. And that equals 37. So I'm just going to divide both sides by negative 37. And I get x equals negative 1. So there's my first coordinate, x equals negative 1. So I know my coordinate pair is going to be negative 1 something. So to find my y value, I'm going to take that negative 1 and plug it in for either equation. So I'm going to choose, I'm actually going to choose this equation right here. Now I know that that equation and the purple equation are equivalent, so I can use that. It's easier, it's already solved for y. So it's going to be y equals 3 times negative 1 plus 2. So y equals negative 3 plus 2. Y equals negative 1. So my coordinate pair is going to be negative 1, negative 1. That's my answer. Negative 1 satisfies both equations. And you can plug negative 1 back in and see if it works. That's substitution. Sometimes substitution works best, sometimes we have a method called elimination, and sometimes it works best. So, elimination, also known as linear combinations, is when you add the two equations together. So I'm going to add one equation to the other, and I want variables to cancel out. But I can also subtract, so I can add or subtract. A lot of people think you can only add, but you can actually subtract without having to change the equation. So I look at this first one. I've got y minus 5x equals 0 and y minus x equals 4. So what I'm looking at is if I do y minus y, I'm going to get 0y. That means my y's cancel and they're gone. And I'm left with only x. So then I have an equation with only x and I can solve for x. So that's what I'm going to do. So I'm going to subtract the second equation from the first equation. So we just do it by parts. So y minus y is 0y. Negative 5x minus 5x. Be careful here because this is negative 5x minus a negative x. So that actually becomes a plus x. And that is negative 4x. So that's minus 4x. And then 0 minus 4 is negative 4. So as you can see, my y's have gone away, and all I'm left with is negative 4x equals negative 4. So it's just one step, divide by negative 4. I get x equals 1. Which again, I knew that because this is the same problem from the first two examples. Now that I have x equals 1, I'm going to plug that back into an equation, And I'm going to choose the second equation just because I don't know, it looks better. So y minus 1 equals 4, y equals 5. Again, my point is 1, 5, which is what I got in the first two problems, or the first two methods. Same problem, first two methods. Number 4. Number 4 is a little bit different because it's not already set up like I can just subtract. So I have to change one of the equations, or change the way it looks, that is. I want to get same numbers here. So I want either a 3 and a 3, or a 6 and a 6, or 2 and 2, or 3 and 3. I want these variables to cancel. So the best way to do that is to multiply this top equation, the whole thing, times 2. So I'm multiplying both sides, or every single term, by 2. And that's going to give me 6x plus 4y equals 12. And the reason I do this is because now I can add these two equations together and get the x's to cancel. So I'm going to do that. I'm going to rewrite this down here. 6x plus 4y equals 12. And I'm going to add these together. So negative 6x and 6x is 0x. That's what I wanted. They go away. Negative 3y plus 4y is just y. And negative 6 and 12 is just positive 6. So this leaves me with my answer. Y equals 6. No other work to be done there. Now that I have y equals 6, I can take that value and plug it back into any of these equations because they're all satisfied at 6. So let's see, I'll choose the purple one because it looks simple to me. So I'm going to take 6 and plug it in for y. So I get 3x plus 2 times 6 equals 6. So 3x plus 12 equals 6. Subtract 12 from both sides. I get 3x equals negative 6. Divide by 3, I get x equals negative 2. So my point that satisfies both of these equations is the point negative 2, 6. That means if I plug in negative 2 for x and 6 for y on any of these, I will get something equal to the same thing, like 6 equals 6 or 12 equals 12, so on and so forth. So that is the linear combination method, and you can add and subtract two equations together or combine them. That's where the linear combination comes from, to solve your equations. Here are two more examples that I want you to solve on your own. Example 5 and example 6, and you can use whatever method you like, but I just want you to solve these on your own, and we'll talk about them in class.